All right, so we're gonna jump back into this conjugation thing. Hopefully you got a chance to watch the video. And I want to go back to one of these examples first, just so you can see the difference in something that's fully conjugated and that's partially conjugated. So, excuse me, on this benzene ring, you can see where there's a p orbital, or everywhere there's a double bond, there's a p orbital on each carbon. And then over here, it's the same. You have the same thing. However, the difference is on this front carbon right here, that's not a p orbital. So this is still conjugated, it's just partially. So this is fully, and then this is partially. Right, but they're both conjugated. So I hope that point was clear from the other day, even though we couldn't like annotate the screen and all this stuff. Well, let's go back to here, because this is an important concept, right? So we talked about how you had these alternating double and single bonds, like so, right? And those two pi bonds are separated by that one sigma bond. And what that allowed for is for these two orbitals right here, right, to come closer together. So the distance between those two carbons shortens. And so that creates this, it creates, instead of a 2 pi, right, so this would be, come on, man. Right, so under normal circumstances, this would be a 2 pi system, and that would be a 2 pi system. I'm gonna change this pen. Right, by 2 pi, what I'm talking about is the electrons in the p orbitals. Right, that's what 2 pi means. So 2 pi, those are pi electrons, or electrons that are in a p orbital. Let me go back to another example, see if we can get some feedback on that. So what type, how many, and you can tell the number of pi electrons by the number of p orbitals. So how many, what type of system would this be right here?
1, 2, 3, 4, 5, 6. So that would be what? 8 pi?
No, it'll be 6 pi. It's a 6 pi system. You got 6 p orbitals. And then that means you got 6 pi electrons. Right? It's that simple. The number of p orbitals is going to be equivalent to the number of pi electrons, unless you're dealing with like a radical, right? And I'll show you an example of that too. So this will be 6 pi. What about this one?
4 pi.
4 pi, good. What about this one? You got a p orbital on each one of these. You can count up the double bonds too. Either way, you'll arrive at the same number. So what is that? 1, 2, 3, 4, 5. So it's a 10 pi system. Very good. Right? The only time you'll have some weird odd number, or because you can have odd numbers. Let's say you have a allylic radical, like something like this, right? Then that would be what? Because that radical is in a p orbital, and then you got a pi bond adjacent to it. So what do you think? And one electron in each one of those.
3.
It's a 3 pi system. That's right. Right. Well, is that making sense? I want to do that first before we move forward, just to make sure that everybody, when I say 4 pi or 6 pi or whatever, you understand what I'm talking about. All I'm talking about are the electrons in the p orbitals in those conjugated systems. That's it. Does that make sense?
Yes.
Okay. All right, so let's go back to here. Right, so you got these 2 pi bonds adjacent to one another, connected by this one sigma bond. And so what happens is all of these orbitals overlap, right? So instead of two pi systems being separate, now this thing is considered what we call a 4 pi system, right? It's a 4 pi system. And so because it's a 4 pi system, there are 4 ways. Let me shorten this up. 4 ways for those orbitals to overlap. 4 ways to overlap. So 4 different combinations. All right. So hopefully you saw the video that I sent out, and it talked about a 2 pi system and a 4 pi system. And so let's just recap that 2 pi real quick. So let's say if I just have just a pi bond like so, that pi bond is going to be composed of 2p orbitals. So that means this is a 2 pi system, and those orbitals can combine 2 ways, right? So what the extension of this is to draw what's called a molecular orbital diagram. Right. And the purpose of that is to kind of be able to dictate or predict the reactivity of these systems, right? Because they don't react the same way as regular pi systems do because they're conjugated. So in this case, you have one molecular orbital that you can draw that way, but because you can combine them 2 different ways, you can also draw another molecular orbital, right? And the way that molecular orbital theory works is that it's basically you are basically conferring like the same properties of a wave and a particle on these particular orbitals. And so if we think about it as a wave, then if you took physics, you know that there's like the first harmonic where the wave never passes through 0. And then you have the second harmonic where the wave passes through 0 once. Then you have the third harmonic where it passes through twice, and so on and so forth. So you can keep doing that, right? You can keep doing that. You can go, the wave will continue to pass through 0. The frequency will continue to increase, so on and so forth. So for this 2 pi system, right, the first set of molecular orbitals, that's going to be representative of that first harmonic where the wave never passes through 0, right? So what that means is that the signs of these orbitals will never change. They'll always be the same. And before we go any further, is everybody okay with the fact that that p orbital has 2 lobes and it has a place in the middle called a node where no electrons can be, and each node has a different sign, right? So we can say positive or negative, or the bottom can be positive and the top can be negative. It doesn't matter. But the point is that the orbital itself has a sign. Each lobe has a sign. Yes or no?
Yeah.
Okay, great. So can somebody tell me why we could say that each lobe has a sign? What is it? Go ahead.
Isn't each orbital have a positive and negative side?
Yeah, but how is that possible? That's the question I'm asking. What is an orbital? Go all the way back to part 1 when we first started learning about orbitals and, well, actually GChem. How is that possible? What is an orbital? Is it real? What is it imaginary?
Isn't the orbital just how the electron travels?
Yes. It's a graph of the path of the electron. Is that right?
Yeah, so I guess if the electron is in one node, then it's going to be negative and then the other one will be positive, right?
Well, the positive and negative is not the charge, it's the sign of the equation, right? That's what I'm trying to get at. If the orbital is an equation, then equations can have a positive side and a negative side. Is that right? Like, let's say,
over here, babe.
say that again.
Over here.
So like if let's say I have a graph of a line on the Cartesian plane, right? this part of that line is going to be negative. Is that right?
Yeah.
And then this part is going to be positive. So any equation can have both a positive and a negative part. All right. All right. So you can unmute yourself if you need to say something. So anyway, going back to the p orbital, right? That orbital has a sign. Okay, so when we look at the 2 pi system right here, right? The first set of molecular orbitals that's here, the lobes on those p orbitals will never change signs because the wave never passes through 0.